Okay, let's talk about exceptions to the octet rule. So remember, the octet rule just basically says that atoms are going to try to obtain 8 electrons in order to be stable. Okay, so they're going to bond in order to obtain an octet. And that could be by actually taking electrons from something, like in an ionic compound, or it could be sharing electrons in a covalent compound. So even if it has to kind of share some of those 8 electrons, they will do that in order to become stable. But not everything in a compound is going to obtain the octet or stop at the octet. It's a pretty good starting place and it helps us understand things about substances. You don't always have to know that something is an exception. You can kind of treat it as if it follows the octet rule, and it can still help you predict things about the shapes of the molecules and the properties of the molecules without even knowing that it's an exception. But let's talk about when things kind of break that rule, when things would be an exception. Um, and so one of the cases is when you have an odd electron species, meaning there's overall an odd number of electrons, okay? Um, and so they're going to have some unpaired electron, okay? So if there's an odd number of valence electrons, then something isn't going to be paired, right? Most of the time when we draw Lewis structures, you're drawing lines to indicate a pair that is being shared, and you're drawing pairs of dots, lone pairs for pairs of electrons. Occasionally, there's an odd number of electrons in some substance that you're dealing with, and that means there's going to be one electron left over that is not paired. Okay, now most often when this is the case, the Lewis structures that you draw are going to have the unpaired electron on the central atom. Um, and really, the reason we do that is because that really is the most likely location of it. That is going to be where that electron is provided the most stability. Because the pairing of electrons, in some sense, is helping to stabilize these things. When you have paired electrons, their spin, kind of their magnetic property almost, is almost canceled out. It helps to stabilize one another because their spin will be opposite. Um, but when you have an unpaired one, you kind of have this almost unbalanced system. And so when the atom or when the unpaired electron is on the central atom, now that electron not only is helping to be stabilized by the positive charge of the nucleus of the central atom, it also is interacting with multiple other atoms. So typically it'll be on the center. So one example of an instance where you have this is NO2. Okay, so NO2, not NO2 minus, so I'm not talking about nitrite ion, I'm talking about nitrogen dioxide, NO2. That has an odd number of electrons because each oxygen brings in 6 and nitrogen brings in 5. And so overall you have an odd number of electrons, and that odd electron is going to end up being on the nitrogen, okay, because that's the place where it is the most stable. But it still is somewhat unstable. So when you have an odd electron species, those tend to be very reactive. Okay, so they don't exist for long periods of time. If there's something around it can react with, it will react relatively quickly. Um, and so really we call these types of compounds free radicals or just radicals. Um, and so those things, they do react quickly. Um, so sometimes when those are formed, since they're unstable, they'll go and react with things, in a way that we don't want them to react, um, because it's just unstable. Sometimes we force the formation of these in order to get some other reaction to occur. So we create this unstable species. That way it'll react with something we want it to react with. So this comes up when you get into synthesis type stuff, or even when you get into biological things. So free radicals can get formed in our bodies, which can be a bad thing. So sometimes something can cause a free radical to form, and it's bad because then it can go and react with something that we don't want it to react with. But in the lab, sometimes we do this just to help us get a reaction to occur. So usually we don't talk about free radicals much at the introductory or general chemistry level. If you were to go into organic chemistry or into biology, then this tends to come up. Um, Now another exception to the octet rule would be when we have incomplete octets. Now, one thing that always has an incomplete octet is hydrogen. Okay, and so hydrogen can only have 2 electrons, so it forms one bond and that's that. That's not actually what I'm talking about, because we have hydrogen in lots of Lewis structures and we wouldn't consider those to be exceptions. Okay, hydrogen's just different. But when we talk about some structure having an incomplete octet, we're really talking about something where the central atom has less than 8 electrons. Okay, now this isn't something that you should be okay with all the time. Okay, when you draw a Lewis structure and you're trying to come up with a valid one, you don't ever stop with less than 8 in the center, unless if you know that central atom is something that doesn't want to have 8. Okay, and so the reason that this would happen is sometimes in your structure you just don't have enough electrons to fulfill an octet. Okay, and so that would be when your structure has less than 8 altogether. You definitely can't fill an octet on every, on a central atom if you don't even have 8 in the structure. Uh, Sometimes it happens for stability reasons. There's some elements that just favor having less than an octet, and that's really the main thing that you need to realize. And so, one example before I move on to these atoms that favor less than 8, I said it may be a result of too few electrons. So one common example of this is if you had NH2 plus, NH2 plus. That's a polyatomic ion. And so this does exist in nitrogen has 5 electrons, each hydrogen has 1, and if it has a positive charge, there's really only 6 electrons in there. So there's no way to magic up an octet out of 6 electrons. Okay, so this is one case it's just forced to have less. Okay, but like I said, there's some elements that just favor this. And one of them is boron. Boron's really the most common one that you would run across that prefers to have less than an octet. It really prefers to have 6. Okay, and if you draw the Lewis symbol of boron, you kind of would see this. So if you drew the Lewis symbol, you'd have B, and then you have 3 dots, right? And those 3 unpaired dots are somewhat an indication that boron's going to favor having 3 bonds. Okay, it can take on 5 to get an actual octet, but that's not the best case scenario for boron. And so it does prefer to have 6. It usually will form 3 bonds. So one example I've got here is BH3. And so that's stable for boron. Now in this one, BH3, you actually only have 6 total electrons anyway. And so you're forced to have that. But you have similar boron structures where the same thing would happen if we had, say, BCl3. That structure would actually end up being boron single bonded to 3 chlorines, and those chlorines each has 3 lone pairs. And so in that structure, if you counted up all the valence, this structure has 24 valence, and that's what I have drawn. Okay, and this would be considered the appropriate structure, the valid one, because boron prefers to only have 6 electrons. Whereas if you were following kind of the standard procedure for drawing Lewis structures, you may come up with instead the structure having boron and it being single bonded to two chlorines, but double bonded to another. Okay, now I know I've rearranged where my atoms were there, just because of where I had space. And so in this, you would also in this structure have 24 electrons, but now boron has an octet. But that isn't very favorable because boron actually is a really tiny atom, and it's not very favorable for it to have 8 electrons crammed around it, or 8 valence crammed around it. So this one would be considered the true structure of BCl3, just like BH3, just having the 3 bonds to chlorine. Okay. A couple other elements sometimes you run across that prefer to have less than an octet, and that would be aluminum and beryllium. Aluminum is very similar to boron. It's directly below it on the periodic table, so it also only has 3 valence electrons, so 3 unpaired electrons, so it would prefer to only form 3 bonds. And then beryllium is a group 2 element, and it only has 2 valence, so it generally prefers to form 2 bonds, thus have only 4 electrons. Now those two you generally don't run across a lot in kind of general chemistry. If you moved on to like organic, you might run into the situations where this happens. But usually when we're dealing with aluminum or beryllium, usually that's in ionic compounds. And in that case, you're not talking about sharing electrons. Okay, so those two you wouldn't run into quite as much. But boron, that's a pretty common one, and it's assumed most of the time that you know that it prefers less than an octet. Okay, now we've got one other scenario, and that's expanded octets. So sometimes you'll have a central atom that actually has more than 8 electrons on it. Okay, this can't happen with everything. Okay, and it does actually have to be a central atom. So that's why usually when you're taught to draw Lewis structures, you're given a particular order to add electrons, and you're told add the electrons on the outside first, and then you put all the extra on the center. And when you add them to the outside, you stop at an octet. You never add more than 8 electrons to an outer atom. Okay, only the central atom. And that's only if you have left over. Okay, other times that you would then add more would be for stability reasons, but that's going to be a little tougher task. Now, this is going to be possible, like I said, it's for central atoms, but only if those atoms are an atom of an element that is on the 3rd row or beyond on the periodic table. Okay, so the 3rd period or below. If it is a 1st period element or a 2nd period element, it absolutely cannot have more than 8 electrons. Actually, 1st period can't have more than 2 because that's hydrogen and helium. And those are super tiny atoms, and so they cannot take on more electrons. But 3rd period and below, so things like sulfur and phosphorus and chlorine and bromine and iodine, those are really common ones to have more than an octet. Or, you'll find scenarios where they have more than an octet. They don't in every structure. Okay. But the reason this would happen is either because there's just too many things attached. So we're typically looking at, you have a central atom and you have things coming off. So if you have 4 things attached, then that's 8 electrons. But if you try to attach a 5th thing, or say a 6th thing, you can only do that if it has more than 8 electrons, because you can't make 5 bonds without using 10 electrons, or 6 bonds without using 12 electrons. It's not possible. And so sometimes there's just too many things. And so one example of that would be PCl5. So PCl5 has 5 chlorines attached to this phosphorus. And so the only way you can attach 5 things to that is by using 10 electrons. So the phosphorus just ends up having an expanded octet because it's holding on to more things. Another scenario where this can happen is if there's just too many electrons, okay? So when you're drawing the Lewis structure, you end up filling an octet on all the outer atoms, and then you still have extra electrons. And remember, you always put those on the central atom. And sometimes that will lead to the central atom having too many, okay, or more than an octet. And so one example of that is when you have xenon tetrafluoride. And so when you draw the Lewis structure of that, you end up attaching the 4 fluorines, filling up their octets, and still having 4 electrons left. And the only place you can put those is on the central atom. And that's okay because xenon is 3rd period or below. Okay, same with phosphorus. It's 3rd period or below on the periodic table, so it is okay that it has an expanded octet. Okay. So those are our 3 scenarios when there can be exceptions to the octet. Typically, when you're getting started with Lewis structures, you follow the octet rule, and that's that. But realize that there are scenarios when that does get broken, okay? But it's really these 3 cases, and there's specifics that kind of tell you when it can happen, okay?